this is Junichiro Horikawa, and this is the 15th episode of VEX for Algorithmic Design, and the topic today is Matrix Basics 1, Transformation Basics. In this session, I'm going to split it into two sections. In the first section, I'm going to explain the basics of matrix, what matrix is, how to do the calculation using matrix in Houdini as well. And in the second section, I'm going to actually show you how you can use the matrix in terms of the transformation, how you can use the matrix for the transformation. And I have titled today's session as Matrix Basics 1 because I have a lot other things to talk about matrix other than the one that I'm going to talk about today. So I'm planning to talk about other topics in matrix which can be used for other kind of transformation other than the one that I'm going to explain today. But I'm going to explain the real basics of matrix in this session. So if you are interested in using matrix for your purpose, for your like geometrical modification purposes, please try to watch this one first, then try to watch the later video that I'm going to explain more about other usage for the matrix. Now, first of all, let me explain what matrix is. Matrix is actually a 2D grid of numbers which can be expressed like this. This is a 2x2 matrix which it has 2 rows and 2 columns. It could be any size for the rows and columns. Sometimes it looks like this, which is 3x2 column, 3 columns by 2 rows, or it could also be like 2 columns by 3 rows. Now, when you have the same number for the rows and columns, it's called as square matrix. Now, in 3D graphics, in most of the cases, you use only square matrix and you don't use much of a regular matrix like 3x2 or 2x3. And in Houdini, there's only 3 types of matrix. One is 2x2 matrix, and the other one is 3x3, and the last one is 4x4. Now, the most used matrix in 3D graphics is actually a 4x4 matrix, which you have 4 rows and 4 columns. That is because it can include all 3 types of transformation. One is translation, one is scaling, and one is rotation within this one matrix, which can be used to transform the coordinate into other coordinate. Now, I'm going to explain the detail about how you can use this for the transformation, but for now I'm going to explain how you can deal with this matrix as the basic. Actually, the matrix itself is just about this grid and nothing more. But there are several rules for the matrix in terms of calculation, so I'm going to show you how those calculation works together by showing the result in Houdini. And in Houdini and in most of the 3D graphics engines, most of the time you only use square matrix. And in Houdini you have 3 types. One is 2x2, another one is 3x3, another one is 4x4. So let me first explain how those 3 types of matrix being expressed in Houdini. Now let's start by matrix 2. I'm going to create a geometry node first. Then inside I'm going to create an attribute wrangle. And let's name this matrix 2. Now when you want to declare matrix 2, you type like matrix 2, straightforward, and then select the name for the variable, like let's name it mat, And in order to create the matrix, it's pretty similar to vector. You use set most of the time. And since the matrix 2 is 2 by 2 matrix, so in total you have 4 numbers. So in order to declare a matrix for the matrix 2, you type 4 numbers separated by comma inside a set function. Okay, and when you want to have this, when you want to set this in a current attribute, let's change this to detail. You use the expression 2 at. This means you are accessing to the matrix 2 attribute, and name the attribute. Like in this example, I'm going to name it as mat, and store this mat matrix 2 that I have just created. Now let's look at the geometry spreadsheet. I'm going to open this one here and go to the detail. You see that you have mat 0, mat 1, mat 2, mat 3, and this is as expressed as one matrix 2, and each index you have these numbers that you have just set right here. So this is how the matrix is expressed in an attribute. Even though this is 2 by 2 matrix in attribute, it doesn't really look like squared grid, but it looks like an array. Now let's also try matrix 3. I'm going to, I'm going to duplicate this one. Okay, it says matrix 3. And for the matrix C3, the type is called as matrix 3. And for this one, since the matrix 3 is 3 by 3, so you need 9 values. So let's add 5 more. And in order to access to the attribute, you use 3 instead of 2 for the 3 by 3 matrix, which is called as matrix 3. Okay, and if you do it, you have 9 array look like values stored as mat inside a detail attribute. Okay, pretty much for this matrix 4, which is 4 by 4 matrix. Let's try to create that as well. For the matrix, for the 4 by 4 matrix, which is not called as matrix 4, but it is actually a matrix itself, since it is the most used matrix type in Houdini and also in 3D graphics. And since that is 4 by 4, you need 16 numbers. So let's add 7 more. Like this. And for the 4 by 4 matrix, in order to access to the attribute with an expression, you type 4 at. And here you go. You now have 16 values to express 4 by 4 matrix in an attribute. Now I have just shown you how you can declare matrix for all those 3 types, but there are actually other ways to declare the matrix. So I'm going to show you how you can declare each of the matrix in different ways. Now I'm going to again create an attribute wrangle, and let's name this, let's run over detail. And first of all, the one that I have just shown you using set is one type, which I have done it right here. So I'm just going to copy this one and paste it like this. So I'm going to create an example using the 4 by 4 matrix. And if you want to bring this to a detail attribute, you type 4 at mat1, mat1. Now that I have 4 by 4 and is equal to 16 numbers, stored in an attribute or detail attribute as a matrix, 4x4 matrix. Now, good thing about using set function is that same as for the vectors, you can use variable inside the parameters. Now, if you don't need to use variables, if you just need to enter numbers instead of using any variables, then you can, the other way you can declare the matrix is same as vectors. You can use curly bracket, and inside the curly bracket you can type the numbers like the same as the set. But remember that if you use curly bracket to declare a matrix, you cannot use variable inside. And let's try to store this in a attribute named as mat2. And here you go. You have these 16 numbers. So let's try to have like variables like val, and let's say 1. And inside set, you can use this variable without problem, but if you try to use this variable inside the curly bracket, it will give you an error. So that's the bit of difference. Now, since this is a matrix, which is a 2D grid, you can also declare a matrix in other way as well, using inner curly bracket for this one. So let me show you an example. Let's name this mat3. And since this is a 4x4 matrix, you can create a pack of vector 4 like this, using a curly bracket, using additional curly bracket inside the outer curly bracket to have 4 numbers inside. And in total you have 4 curly brackets inside the outer brackets. And this could also work to declare the matrix. So you have 4 numbers packed in curly bracket each. And I have just named it mat3, and if you store this in mat3 attribute, you still have the same matrix stored in an attribute. So this could also work, but same for the second one, you cannot use variable for this one since this is expressed using a curly bracket. Now the same idea can be applied for this set type. So you can create a matrix using an inner set, using additional set inside the parameter like this. Oops, I have missed 4 right here. Like this. And this could also work to declare the matrix. You have 4 sets, and each set function you have 4 numbers, which is equivalent to creating vector 4. And you can say that you have 4 numbers of vector 4 for this one. And the result is pretty much the same. You have 4x4 matrix can be stored in as an attribute like this. So any way to declare the matrix is fine, using set or using curly bracket or using double curly bracket or double set. Either way works just fine. Now let me rename this to declare matrix. Now actually when you create a matrix, Most of the time you don't do like this, but when you start from a basic matrix, you use something called identity matrix. Let's see what this identity matrix is. Now, identity matrix can only be used for the square matrix, which is for 2x2, 3x3, and 4x4. And it looks like this. For 2x2, it looks like this. For 3x3, it looks like this. And 4x4, it looks like this. If you look at carefully, you have a diagonal position in each matrix has a value 1, and for the other part it is 0, all 0. And only this diagonal places you have the value equal to 1, and this is called as identity matrix. And this this matrix form is pretty important and is going to be the base for the transformation, for all the transformation using matrix. So remember that this is pretty important for now. And you'll use this a lot later on for the transformation. And you'll be able to understand why the identity matrix looks like this. Now let's see how we can create this identity matrix in Houdini. So I'm going to create another attribute, triangle. Let's name this identity. Use it for detail, and it's pretty simple. There is a function in Houdini, VEX, which is called as ident. And this is the one that you can create identity matrix. And let's try to see how it looks like in an attribute. And you can see that the first 4 is the first row, and the second row is this one, and you have 1 on the second column here. And for the third row, you have a value 1 in third column, and the last row you have 1 in last column. So you can see that the value 1 is placed on a diagonal position of the matrix. If you want to make 3x3 matrix, or if you want to make 2x2 matrix identity matrix, then you can just change the type here to matrix 3 and 3 at mat, and you'll be able to create a 3x3 matrix identity matrix. If you just change this to 2 and 2 here, you can create 2x2 identity matrix just like this using the same function. But most of the case you would like to use 4x4 for all sorts of flexible transformation. Next, let's look at some special numbers which you could only get from a square matrix, which is called as determinant. Now, determinant is a float number and which you can calculate from a square matrix. And let me give you an example for the 2x2 matrix. So let's say if you have a 2x2 matrix looks like this, and the determinant, which often being written like det, can be calculated like this: a multiplied by d minus b multiplied by c. And one of the usage for this determinant is to check whether this matrix has a inverse of the matrix or not. Now, inverse of a matrix is expressed like this. If you have a ABCD 2x2 matrix, the inverse of matrix can be written like this. So let's say this is M, then the inverse of the matrix can be expressed as like this. And what this inverse matrix does is that when you multiply this matrix together with this inverse matrix of the original, like this, you get an identity matrix, which we have seen it, which looks like this. So this is how this inverse matrix works together with the original matrix. And this determinant can be used to check whether this matrix has an inverse matrix or not. Now, most of the time when the determinant is equal to 0, that means there is no inverse matrix for the original matrix. If the value is not equal to 0, then a lot of the cases you have the inverse matrix of the original matrix. Then you can get this inverse identity matrix, which could be really useful when you get used to the matrix calculations. Actually, you don't use this a lot for the matrix basics, but it is a good idea to remember what determinant is, how you can calculate the determinant, and what could be used for. In this case, one of the usage is to check whether the matrix has an inverse matrix or not, by checking if the value is equal to 0 or not. If it's equal to 0, then the matrix doesn't have any inverse matrix. If the value is not equal to 0, then there is a chance that the matrix has an inverse matrix. Now, if you want to calculate the determinant for a 3x3 matrix or 4x4 matrix, what you need to do is pretty similar to a 2x2 matrix. A, B, C, D, E, F, G, H, I. So let's say you have a 3x3 matrix like this. And what you need to do in order to calculate the determinant, one quick way to remember how you can calculate is to first add a similar number or same numbers, same matrix on next as a guide, and then pick up 3 diagonal values, which this one, and this one. And you're going to multiply all these values for the diagonal values and add them together. And next thing you would like to do is to get the other diagonal values, which is this one, and this one. And for these ones, you also multiply these together and subtract with the first added value. So as a result, the calculation for a 3x3 matrix determinant looks like this: A, E, I plus B, F, G plus C, D, H minus H, F, A minus I, D, B minus G, E, C. So this is going to be the determinant value for the 3x3 matrix. And the way to calculate the 4x4 matrix determinant is pretty much the same as 3x3 matrix. You create a copy of matrix on next and create a diagonal to create the equations like these. Now this determinant value can easily be calculated using a function in Houdini, so let's see how we can do that. I am going to create another matrix. Let's copy one of the value here. Okay, let's this one. And let's name this determinant. Okay, and let's keep this last matrix value, and let's rename this to mat. Okay, now this is a 4x4 matrix, and in order to calculate the determinant for this 4x4 matrix, first of all, let's create a variable like named as det and use the function called determinant. And inside the parameter, you type one of the square matrix type, matrix 2, matrix 3, or matrix, which is 4x4 matrix. In this case, I have 4x4 matrix here, so let's enter this one. And as a result, you will get a float value, and let's see how this value looks like by having it inside a detail attribute. Okay, I think I have to make this one. Now, as a result, if you look at the geometry spreadsheet and go to the detail section, and for the attribute, you have this attribute called det, and it says the value is 0. As I have told you, when the determinant is equal to 0, then there is no such inverse matrix available for the matrix that you have calculated the determinant. So the determinant value is currently 0, so this means is that this matrix does not have any inverse matrix. Now let's try with other kind of matrix which would have a inverse matrix. So let's create another matrix. I'm gonna name this mat2 and try to create a matrix which has a determinant value other than 0. So let me try creating, I'm going to randomly set some numbers like these. Might or might not create 0, but let's see. Okay, and let's try to calculate the determinant for this matrix. I'm gonna name this det2 with a determinant function. That's for the matrix 2. Let's give this as an attribute. Okay. Now it has a value which is other than 0. Currently it says 558.6. So since this is not equal to 0, which means this could have a inverse matrix. Now let's check if this determinant is valid to check the inverse matrix, if the matrix really has an inverse matrix or not. There's also a function in Houdini VEX to create an inverse matrix out of the original matrix. So let's try to use that to check if you can really create an inverse matrix or not. I am going to duplicate this node, and for this one I'm going to call this inverse. Now in order to create an inverse matrix from the original matrix, what you can do, first of all, I'm going to name the created inverse matrix as imat as a variable. Then use the function called inverse or invert. Inside this invert matrix, invert function, you type the matrix that you want to create an inverse matrix from, and as a result you'll be able to get the inverse matrix. Now in order to check if this matrix that I have created using this invert function is really an inverse matrix or not, the easiest ways to check is to multiply this matrix together with this inverse matrix and see the result, if the result is really a identity matrix or not. Okay, so let's try to see that. Let's try to multiply these two together by mat multiply by imat, and name this as other matrix like cmat, and let's store this in a attribute, detail attribute. Okay, so for at cmat is equal to cmat. Now if you look at this cmat 4x4 matrix, it is obviously not an identity matrix. The identity matrix was only diagonal positioned numbers. When the column and row number is the same, the value is equal to 1, and for the other values it should be 0, but as you can see this is not the case here. So the one that I have got here using the invert matrix is not actually a inverse matrix of this mat. And you couldn't create the inverse matrix, and that was because the determinant was equal to 0. Okay, so let's check for the other one, the matrix 2, which is not, which the determinant is not equal to 0. So in theory, you should be able to get a identity matrix, or you should be able to create a inverse matrix out of it and be able to multiply these two matrices together, the matrix 2 and the inverse matrix of this one, to create a identity matrix. Okay, so let's try. Matrix I mat 2 is equal to invert mat 2, and I'm going to create another matrix to check, which should be is going to be calculated as identity matrix, which is going to be mat 2 multiplied by I mat 2. Let's store that result to cmat2 attribute. Okay, now if you look at it, now let's open this up. Now from here to here, this is the 16 numbers, which declares the 4x4 matrix, and start with 1 and 0, and you see that these numbers are not equal to 0, but it's pretty close to 0, which is, it says 7.45, but have an E minus 8, so which is pretty close to 0 value. And these are the same, and you have a 1. So the first 4 column, you can say that you have 1 0 0 0, and for the second row you can say you have 0 1 0 0, and for the third row you can say 0 0 1 0, and the last one can be set as 0 0 0 1. So you can say that the value that you have got as a cmat2 is equivalent to the identity matrix. When the determinant is not equal to 0, which in this case 558.6, you'll be able to get the correct inverse matrix, and if you multiply the inverse matrix with the original matrix, you'll be able to get this identity matrix, which is pretty useful factor to remember. I mean, most of the cases when you use matrix in Houdini, you're going to use the prepared functions like rotate, scale, and translate, so you don't really need to care about those determinant or inverse matrix. But if you get more used to the matrix process or calculations, knowing how this determinant is being calculated and how you can use it, what you can use this for, is pretty important. So for now, try to remember what it does, what it's for. And actually, there's a lot more information you can get from this determinant value, but in this matrix basics sessions, I'm just going to say that the determinant can be used to determine whether the matrix can have an inverse matrix or not. Now let's see other well-used process for the matrix, which is called as transpose. Let's say you have a 3x3 matrix, A, B, C, D, E, F, G, H, I. And when you say you want to have a transpose matrix of the original matrix, let's say this is M, the transpose matrix can be written like this, having T on the right top bottom, right top corner, and which can be written like A, B, C, D, E, F, G, H, I. So this means is that the rows and columns has been switched, so that the first row used to have A, B, C, but by transposing it, you'll be having this A, B, C in a column. C, A, B, C becomes the row becomes column, and the second row becomes the second column, and the third row became a third column. So this process is called as transpose. Now the usage for the transpose is not obvious in basic transformation using matrix, but it's going to be useful when you do a bit more complex transformation like projecting and so on. In today's session, we're not going to use this transpose that much, but it's a good idea to remember what transpose is about to understand the basic idea. Now, in terms of calculation, the transpose have some characteristic. When you have two transpose matrix, let's say one of the matrix is called as A and the other matrix called as B. And when you have a transpose A and transpose B, and if you multiply them together, it is equivalent to B multiplied by A and transpose. Now you can see that on the right hand side, the order of the matrix multiplication is different from the left one. And in matrix calculation, in matrix multiplication, when you change the order, then the result value is going to be different as well. And I'm going to explain the detail about this multiplication order later on. But just remember that when you use the transpose, this kind of role exists. A transpose by B transpose is equal to B multiplied by A transpose. Now let's see how we can create this transpose matrix in Houdini. There's just a function for it, so let's see how we can use it. I'm going to copy this determinant attribute wrangle, and let's name this transpose. Okay, and I am going to delete all the values here. And first of all, I'm going to create the attribute for the detail called mat and store this original matrix to the detail. Okay, and next I am going to create another attribute called as tmat, and for this one I would like to apply a store the transpose matrix. In order to create the transpose matrix out of the original matrix, you use the function called transpose and use matrix inside the parameter. And as a result, you'll be able to create a transpose matrix instantly. And if you look carefully, the first row became 1, 5, 9, 3, and the second row became 2, 6, 10, 14, and so on. And if you look at the first value of the column, for the first column values, it is 1, 2, 3, and 4, which was previously a number for the first rows. So as you can see, the matrix has successfully been transposed using this simple function. Now that's much it for the transpose. Let's go to the next one. Now what I'm going to explain next is the pretty important stuff, which is the calculation for the matrix, the basic calculation for the matrix, which is the multiplication for the matrix. Now there's three types of multiplication for matrix. One is matrix multiplied by scalar value, meaning a float value. One is a matrix multiplied by a matrix itself. And the other one is matrix multiplied by a vector. So there's mainly three types of multiplication, which all of them are pretty important to know how it's being done. So let's see one by one how we can do this. First of all, let's look at the multiplication between matrix and scalar value, which is pretty simple. Let's say if you have a matrix 3 by 3 matrix, looks like this. and you have a scalar value like k. What you're going to do is to multiply this k value with every element inside the matrix. So it looks like this. And the result you get is the same matrix shape. If it's 3 by 3 matrix, then you get the 3 by 3 matrix as an output. Okay, so the result for this one should look like this. So every element has been multiplied with the value k. That's how multiplication between the matrix and scalar value works. Now let's see how we can do this in Houdini. First, I'm going to create a attribute wrangle again. I guess I'm going to just to duplicate one of the node here. I'm just going to duplicate this transpose node, and let's name this multiplication with Scalar. Okay, and first of all, let's say that I have a 4 by 4 matrix like this one, and let's try to multiply this with some scalar value. So in this case, a float value. So I'm going to create a parameter called num. Let's promote this. Okay, this one. Let's have this value in between 0 to 10. And the value that I have updated will going to be stored as an attribute called mat in the detail. And let's just delete this one for the transpose. And let's see the result. So if it's 1, you get the same value as the original matrix. If you say 2, all those elements, all those values which is inside the matrix has been multiplied by 2, and you get this result. So it's pretty straightforward. All those values inside the matrix will be multiplied with a single value. That is the multiplication for the matrix with a scalar value. Now next, let's look at the multiplication between the matrix and the matrix, which is going to be the most essential calculation for the matrix. Now for the geometrical purpose, the matrix contains a lot of transformation information, and by multiplying multiple matrix, let's say you have A, B, and C, and by multiplying these matrix, you are adding the transformation one by one. Let's say the first one is for the translation, second one is for the rotation, and third one is for the scaling. By multiplying the matrix one by one from the order, from the left to right, it means that first you do the translation, then after this you do a rotation, then after this you do a scaling. So that's what it means for the multiplication for the matrix, and that it also means is that by changing the order of this multiplication, let's say like B, A, C, you get a different kind of result. If the B is for the rotation, and if the A is for the translation, if C is for the scale, you get the totally different result. It might be more clear to see it in a sketch. Let's say you have a box like this one, right? And let's say the first multiplication is translation, rotation, and scale. Okay, so when you do the translation, maybe you want to move this box to some direction and move it right here. And after it has been moved, for the rotation, you're going to rotate this box using this position, this center, which is counted as 0, 0, origin of the space, and you use this origin of the space to rotate the box. so would come somewhere like this using some angle. Okay, and after this you do a scaling again using this pivot or the origin of the space to do the scaling. And if you do the scaling for this box from this pivot position, it looks, and let's say you want to do half size scaling, the position of the box will go close to the center, and the size also gets half size like this. So as a result, using those three transformation matrix multiply all together, you have just changed this box to something like this in this order. Now, what if you change this order completely in a completely different order? Like let's say C, B, A, and the C is for the scale, B is for the rotation, and the A is for the translate, starting from the same box in the same position, which is 0, 0. Now, since this starts from a scaling, it starts to shrink at half size at this same position, like this. Okay, and then it rotates. Let's say this is around 30 degrees, and which means it rotates using this center position right here, so it looks like this here. It just rotated at the same position by 30 degrees. And then last of all, it is using the translate to move the box in this case, X direction, and as a result you get this result. So even though you are having the same three matrix, by changing the order, the result you get is totally different. So that's what it happens using the multiplication for the matrix. You are adding the transformation, I mean in terms of the geometrical modification, you are changing the order, you are changing the transformation by multiplying all these values together. You are adding the transformation one by one by multiplying at different types of transformation matrix. And it is often written as a 4x4 matrix. You could also use 3x3 matrix or 2x2 matrix for some purposes. Like 2x2 matrix can be used to declare the 2D rotation. 3x3 matrix can be used to declare a 3D rotation, but 4x4 matrix can be used to declare all rotation, 3D rotation, translation, and scale at the same time. So most of the time in 3D graphics, it's pretty common that you use 4x4 matrix. Now that you have some idea what multiplication do for between matrix and matrix, let's see how actually it works. I'm gonna start with the simple example by using 2x2 matrix. And let's say we have two matrices that I want to multiply. So A, B, C, D, E, F, G, H. So let's see how we can multiply these matrices together and what it's going to be the result. Now when you do the multiplication between two matrices, especially for these square matrices, first you pick up the first row, and then for the first matrix, and for the second matrix you pick up the first column. And then what you do is to multiply the first item in a row and first item in a column and multiply these together. And you do the same for the second element in a row and second element in a column and multiply these together. And what you do next is to add those values together. So A multiply E plus B multiplied by G. And that result is going to be the new value for the first row and column value. So the value that you have just calculated is going to be set as this capital A value. And mostly for the other part, you do pretty much the same things. For the B value here, you've again pick the first row, and then next you pick the second column in a second matrix and do the same calculation, A multiplied by F plus B multiplied by H, and that is going to be this B value here. And for the C value, you then pick the second row and pick the first column and do the same calculation, CE plus DG. And for the D, pick the second row and the second column and do the same calculations. So as a result, it looks like this: AE plus BG for this first item, and AF plus BH, and this one CE plus DG, and this one is CF plus DH. So this is going to be the result of the multiplication between two matrices, especially if it's the square matrix, the multiplication between square matrix. Now the same idea can be applied for other square matrix for 3x3 and 4x4. If it's 3x3, you have two matrices having the same rows and columns. Like this. And what you do is pretty similar to 2x2 matrix. You pick up the first row and first column, multiply these values and the numbers in the same index. So A multiplied by J plus B multiplied by M plus C multiplied by P will going to be the new value for here, this position. And do the same for all these values. Now in this case, the first value is going to be, this one is going to be AJ plus BM plus CP, right? So what if we change the order of the matrix like this? If this J, K, L, M, N, O, P, Q all comes on the left hand side, and on the right hand side we have A, B, C, D, E, F, G, H, I. Then if we try to do the multiplication in the same manner, picking this one and this one, then the value that we get is AJ plus DK plus GL. So as you can see, the result you get is different, even though you are you seem to do the same multiplication between the matrix. So the order matters in terms of matrix multiplication. Now you don't use this a lot for 3D graphics, but you can also multiply between a non-square matrix, like if you have 2x3 matrix, then you can use this to multiply with the matrix looks like this one. In this case, you have 2x3 matrix on the left hand side, and for the right hand side you have 3x2 matrix. Now the reason why it looks like this, when you have a 2x3 matrix on the left hand side, you have to have 3x2 matrix on the right hand side. That is because, as we did for the 3x3 or 2x2 or 4x4, we have to give a group for the multiplication like this. For the first row, we pick AB, and for the first column, for the second matrix, I pick G and K and multiply AG and add it with the BK. Okay. So as a result, what we get is AG plus BK for the first item, and for the second item it's going to be DAB with HL. So AH plus BL, and for the third one, AI plus BM. Okay, and do the same for the other values, like this one is CG plus DK, CH plus DL, CI plus DM, EG plus FK, EH plus FL, and EI plus FM. So previously it was 2 by 3 by 3 by 2, and the result became 3 by 3 matrix, meaning it is using the column number for the first matrix, which is 3, and the row numbers for the first matrix and the column number for the second matrix, and that is the result that we get, 3 by 3 matrix. Now if we think the other way, if we have this 3 by 2 on the left hand side and the 2 by 3 on the right hand side, what do we get? So GHI, KLM, and A, B, C, D, E, F. Now in this case, on the right hand side you have 2 rows, and on the right hand side on the matrix you have 2 columns. So as a result, what you get is a 2 by 2 matrix as a result. So in this case, what you do as a multiplication here is this rows multiplied by this rows. So AG plus CH plus IL for the first one, and do the similar calculations for this one, this one, and this one. Just remember that the number of rows and columns for the output depends on the numbers of rows and columns on the left hand side and right hand side. Now we don't use this kind of multiplication in Houdini that lot because there is no type for this kind of matrix 3 by 2 or 2 by 3 or any unsquare matrix. So for now you can just remember that how this multiplication works, and you don't really need to you're not really going to use this inside Houdini that much. If you're familiar with Python, you'll be able to create this kind of matrix in Python to do some related process. Most of the time and recently you use this kind of stuff in machine learning these days, I think, but probably there are more. Now let's actually try to do this calculation, the multiplication between the matrix and matrix in Houdini. In this case, in Houdini, there's only a square type matrix, so let's try to do a multiplication between a square matrix by square matrix. And let's do the matrix multiplication between a 4 by 4 matrix, shall we? So I'm going to duplicate this attribute, wrangle, and so let's say this is the first matrix that I want to multiplicate, to do the multiplication, and let's create another matrix for the multiplication. Let's name this mat2 and set using set. And inside the set, I'm going to create for set value, and I'm just going to make a value which is starts from 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, and 4, 3, 2, 1. Now let's calculate the multiplication between those two matrix, which is pretty easy to do. Let's create a mat3 variable called mat3 and multiply mat1 by mat2 like this. Now let's also try to do the multiplication in different orders. So mat2 by mat1. So matrix 4. Mat4 is equal to mat2 multiplied by mat1. And what I want to see here is the result is different. Okay, so let's store all those two matrix inside a detail attribute. So mat3 for the mat3 and 4 at mat4 is equal to mat4. Okay, so first 16 values are the mat3 here, which is mat1 multiplied by mat2. And you have these values here based on the equations that I've shown you on a sketch. And if you look at the second matrix, which is mat4, which is here, which is mat2 multiplied by mat1, you see that the value is different from the mat1, mat2. This one, which indicates that the matrix multiplication order really matters. Now let me change this to matrix multiplication with matrix. Now I have just shown you the basics of multiplication for the matrix. Now let's see what if we multiply one of the matrix with identity matrix and see what happens. Now to make it simple, let's start by thinking about the 2x2 matrix. We have a 2x2 matrix looks like this, and you want to multiply the identity matrix, which I've told you that this is going to be the basics, the base for all the matrix transformation. And if we try to do the matrix multiplication between those two, let's see how it goes with the result. Now this is going to be AB and 1, 0 for the first value. So the result, which is going to be A multiplied by 1 plus B multiplied by 0. So it's 0. So for the right top corner, which is going to be A multiplied by 0 plus B multiplied by 1. Okay, for the left bottom corner, which is going to be C plus D multiplied by 0. And for the right bottom corner, which is going to be 0, C multiplied by 0 plus D multiplied by 1. So if you make it clear, it's A, B, C, D. So it's the same value as the original matrix. So whatever matrix you multiply with the identity matrix, you get the same result. So that's what identity matrix stands for. Whatever matrix you multiply, you get the same value. And this is true even if you change the order of the matrix. This matrix, bring this to the left hand side, this same rule still works. So let's try to bring the identity matrix right hand side. Like this, and try to do the same multiplication. Now as a result, you get is A plus 0 multiplied by C. So, and for the right top corner, which is going to be B might multiply by 1 plus a 0 multiplied by d. So it's like this, and for the left bottom corner, which is going to be 0 plus c, and for the right bottom corner, which is going to be 0 plus d. So as a result, you still get the same value. So only for the identity value, even if you multiply the if you try to multiply this identity matrix to the right hand side and right hand side, you still get the same value, the same original value. So when you create a matrix, you often start by creating an identity matrix and add additional matrix by multiplying additional matrix to the identity matrix to build up the complex transform matrix. So consider every time you create a transformation matrix, you start with the identity matrix. That's what I do a lot in Houdini for the transformation. Now let's try to do this multiplication between the original matrix with the identity matrix inside Houdini. So I'm going to duplicate this one, and let's rename this with identity matrix. Okay, and for the first matrix, I'm going to keep it like this one for the 4x4 matrix, and for the second one, I'm going to use the function ident to create a identity matrix for the 4x4 matrix. Now do the same multiplication like this, and let's see the result for the mat3 and mat4. And if you look at the mat3, it is completely actually the same matrix value that I have here. And if you look at the mat4, it is also the same value, which is the original matrix. So multiplying the identity matrix with a other matrix just give you the original matrix value, even if you change the order, which is also a pretty important aspect of the matrix multiplication or calculation. Now I've also explained that if you have two matrices multiply together, which is the transpose of the original matrix, is equivalent to this B multiplied by A transpose. So let's try to see if this is also true by trying to calculate this in a Houdini using a transpose function and multiplication. Okay, so I'm going to duplicate this Rango node here, and let's name this multiplication with Transpose Matrix. Okay, so I have two matrices here. So what I want to do first is the multiplication between the transpose matrix for each of the matrices, like this. And for the second one, I'm going to change the order like this and create the transpose for whole result. And let's see how the result looks like for mat3 and mat4. Okay. Now for the mat3, first of all, it starts with the 386 and 274 and so on. If you look to the mat4, it actually shows you the exact same value as the mat3. So seems like the transpose of the mat1 and transpose of mat2, the multiplication between those two matrix and the transpose of the already calculated matrix multiplication is the same value. Now you're not going to use this rule that much for the basic transformation, so I'm just going to keep this as a rule to show you that this kind of rule exists. But for practice, you can ignore this for now, for basics, which I myself don't use this rule that much. Now that was the multiplication between the matrix and matrix. Now the last multiplication type is going to be the multiplication between the matrix and vectors, which is also really important when it comes to geometrical operations in 3D graphics. Vector in 3D space is often used to declare the direction or the position. And by using matrix multiplication with the vectors, you can actually use the matrix as a transform matrix to change the coordinate of the vector. So a multiplication between matrix and matrix give you a addition for the transformation. You can compound the complex transformation, but when it comes to the multiplication between the matrix and vectors, this means you are modifying the vector position or position of a point or a direction of the vector using this matrix that you have created to transform from one coordinate to another coordinate, which sometimes is a translation, sometimes a rotation, sometimes scaling, and so on. Now the rule for the multiplication between the vector and matrix is pretty much similar to that of matrix by matrix. What you need to do is to consider vector as a 3 by 1 or 1 by 3 matrix. For example, you can say, let's say you have a vector called x, y, z. Then you can declare this as a matrix. Looks like this 3 by 1 matrix. And for this one, you can multiply 3 by 3 matrix like this on the right hand side. This multiplication is possible because you have a number of rows, which in this case 3, and number of columns for the right hand side, the same numbers. So this kind of combination works. And same for the multiplication between the matrix and matrix. The result you get is the column number for the first matrix, which is 1, and the row number for the second matrix, which is 3. So which is going to be a row 3 and column 1 matrix like this. Okay, and if you actually calculate this, it looks like this. So the only rows will be calculated together with each of the columns. As a result, you have 3 column values, and each of the value looks like this. So for the first one, ax plus dy plus gz, and the second value bx plus ey plus hz, and the third one cx plus fy plus iz, like this. As a result, you have created a new vector, which is actually a translated or transformed vector. The coordinate has just been transformed from xyz to the new xyz value, the new position for the xyz coordinate. And this is actually what matrix does, a transformation matrix does for the vectors. Now you can actually calculate the matrix between the VEX in a different order. In this case, let's say you have a 3 by 3 matrix on the left hand side and you have a vector on the right hand side. Now on the right hand side, in order to be able to multiply with the matrix, the vector has to be, looks like this. In this case, 1 by 3 matrix. And the calculation will be this rows, the first rows with the column, the second row with the same column, and the third row with the same column. And as a result, you get ax plus by plus cz dx plus ey plus fz and gx plus hy plus iz. Now if you look at the left hand side and the right hand side column numbers and row numbers, the first matrix has 3 rows and the second matrix has 1 column. So the result is 1 by 3 matrix. Okay, and the calculation is going to be, it looks like ax multiplied by by multiplied by cz for the first row, and dx plus ey plus fz and gh plus hy plus iz. So it is still a vector value, but the result you get is different by changing the order. Previously you have x, y, z here, and the result you get for the first value and second value and third value was different. So for the multiplication between the matrix and vectors, the order is also important. And in 3D graphics engines, by using different types of programming languages, the multiplication order between the vector and the matrix varies. Actually, it is dependent on how this programming language express vector in terms of the relation between the matrix. Now in some languages, like in OpenGL, you use this column-based vector. But in some languages like DirectX, you use row-based vectors. And if you use the row-based vectors, you multiply vector with a matrix. If you use column-based vectors, you use matrix multiplied by vectors. So you gotta remember which one is used for the language you're using in order to do the correct transformation. And in Houdini, the row-based vector is used for the VEX. And it's a bit weird, but you can in VEX, I think it's a special case in VEX, but you can actually multiply vector by matrix, or you can also do matrix by vector, but can get the same result. But usually if you're using the row vector, the vector has to be on the left hand side for the multiplication, and the matrix should go on the right hand side. That's the basic rule. That's the base rule. In Houdini, it's a bit special. You can place vectors on left hand side and right hand side, but can still get the same result. Now you might have some questions. What if we use the 4x4 matrix? Currently we only have like x, y, z for the 3D space points coordinate, but if there's only 3 values, then how is it possible to multiply between the 4x4 matrix? Now I'll show you how. When you are using 4x4 matrix, what you use as a coordinate looks like this: x, y, z, and you have 1 or 0 for the first value, and you have a 4x4 matrix: A, B, C, D, E, F, H, I, J, K, L, M, N, P. Now what this 0 or 1 means for the false numbers for the vectors, it is to declare either this value is used for the position or the direction. If it's equal to 1, if the fourth number is equal to 1, then this means this value is position. If it's using 0, then that means it's using direction. Now in Houdini, you can actually multiply directly together, directly between the vector 3, between the 4x4 matrix, without having a fourth numbers. I think in the backend it's converting this to a vector 4, which with a value 1 at the end at the fourth numbers. So if the vector 3 is x, y, z, it automatically converts to x, y, z 1 and use it with the 4x4 matrix. And this process is hidden, but in reality, if in more low-level programming languages, you have to use this kind of calculations. And the order is pretty important as well. Like if you're using like Python to do the matrix multiplication. But in VEX, lucky enough, you can kind of ignore this fourth numbers and just use x, y, z value to multiply with the fourth 4x4 matrix, and the order is not, it doesn't matter as well. So you can bring this vector value to the right hand side as well to do the same transformation for the vectors, which is pretty convenient. But at the same time, if you want to do some special case matrix operations other than like geometrically related multiplication, then it's a bit hard to get the result. So in that case, you need to use like Python languages. Now let's actually try to do this multiplication between the matrix and vectors in Houdini. So I am going to copy one of the attribute Rango again, and let's name this multiplication with vector. I'm going to delete one of the matrix and keep just one matrix. I'm going to name this mat. And also let's try to create a vector value, vector v, and let's set it as 1, 2, 3 to make it simple. And as I told you, the multiplication between the vector and matrix always give you the vector as a result. So for the result, let's give a vector variable named v1, and let's calculate v multiplied by mat. Okay, let's also try to do the multiplication between the same numbers but in a different order to see if we have the different values or not. In theory, it should give you this different result, but in Houdini it gives you the same result, the same transformation result. Okay, so let's try to see that in a detail attribute. For the first one, I'm going to name it as v1. For the second one, I'm going to name it as v2. And let's see. So for the v1, it says 51, 58, 65, and the second one, it also says 51, 58, and 65. So even though if you have changed the order for the multiplication between the matrix and vectors, you still get the same result. And what it's actually doing here is that it's transforming this original coordinate into other kind of coordinate using this matrix as a transformation matrix. Since the purpose of the matrix in Houdini's VEX coding is to transform the coordinate most of the time. Now that's pretty much for the basics of the very basics of matrix, what matrix is, how you do the multiplication between the matrix and vectors and scalar values. Now next thing I would like to show you is how you can actually use this matrix as a transform matrix to transform the coordinate, the vector coordinate, using some of the really useful functions from VEX to do some basic transformation like translation, rotation, and scaling by understanding the basic idea of matrix multiplication. Now the first transformation I would like to show you is the translation translation, and that is to move one point, let's say 1 point, to some direction. with a vector value A, B, C. Now the translation seems pretty simple enough. You have already done this transform for the vectors. You just have to have the point position and add this vector with the this vector direction where it's going to move. Now you can actually express this in a matrix as well. But most of the case, if you only have a transformation, you don't really need to use matrix, but you can just use this vector to add it to the point coordinate. But if you have a complex transformation and in between you have translations, you might want to use matrix instead of using the simple vector addition to translate the point to another coordinate. So it is used in order to do the translation, you use 4x4 matrix, and the base base of the matrix looks like this. So first of all, you start with the identity matrix. In diagonal places, you have 1 value, and for these column values, it's mostly 0, but only for the one on the last rows. For the first, second, and third column, you have a value where you want to where it's used for the vector translation. So in this case, the vector is A, B, C, right? And let's say the original point position is X, Y, Z. So as a result, the translated point position, let's say N, is equal to X plus A and B plus Y and C plus C if you just do the simple vector additions. Now let's see if we do the calculation between the X, Y, Z, 1 by 4 vector multiplied by this 4x4 matrix. And if we get the same result, then this translation is actually working. So let's see if it really does. So this will be the first row, and this will be the first column, which is going to be the X value. So let's see. So X plus 0 plus Z multiplied by 0, 0, and 1 multiplied by A, so plus A for the first one. For the second one, X multiplied by 0, so that's 0, Y multiplied by 1, so Y. Z multiplied by 0, 0, so B multiplied by 1, so you have B. And third one, X 0, Y 0, Z plus C. And for the last one, 0, 0, 0, 1. So the result you get is X plus A, X, Y plus B, Z plus C, and 1. And you can kind of ignore the last values, and if you do the multiplication between 3 by 4 by 4 matrix in Houdini, you get 3 by 3 result. So if you compare those two vectors together, actually it looks just the same. Okay, it's a bit, looks X plus A, Y plus B, Z plus C. So it's the same value you get. So by creating a matrix like this, you can do a translation, which is similar to adding a vector value to a position coordinate. So let's try to create this translation matrix in Houdini and how this works. Now I am going to create a sphere. Let's make this polygon and show the scene. Okay, let me also show the wires. Okay, now for each point I'm going to try to move at some direction with some vectors. So let's say translate. Okay, and first thing first, let's create a vector where we want to move the point to. So chv move. So I've just created a vector parameter. So let's set some random values for x, y, and z. Maybe I'm just gonna say 1, 2, and 3. Okay. Now, next thing I would like to do is to create a translate matrix. And if you go to the VEX Function page and search for translate, you'll be able to find a function called translate, which is explained as translate a matrix by a vector. If you go there, you have a translate function with two parameters. One is the output parameter for the matrix, so whatever matrix you input here will be updated using this translate function, and the amount with a vector 3 or vector 4 value. Now I guess I can use this one, the first translate one, and it says I can update the matrix by a vector. So for the first matrix that I'm going to input inside translate, it should be the most basic matrix, which is not going to affect the transform. So that is equivalent to the identity matrix. So first of all, first thing I would like to do is to create the identity matrix. So matrix mat is equal to ident. So start with this identity matrix. I'm going to translate this matrix by a move vector value that I have declared here as a parameter. Now that I have this matrix being updated to translate from one point to another using this vector, I can use this matrix to actually change each of the point on this sphere to move. And in order to do that, what you just need to do is to multiply the vector, which is the point position here, with this matrix. So at P is the current point position, and by multiplying this current position by the matrix, updated matrix, which is going to be the translated matrix, you are actually moving the point position, every point position in the same direction. If you change this one, you can see that the sphere position is changing based on this matrix value or the vector value, which is then translated into matrix and multiplied with the point. Okay, so currently I just have a z directional values here, and it still works just fine. Now, as I said, if you are just doing the translation, using matrix doesn't really make sense, because it's a lot of coding here, a lot of lines here. So if you're just moving, you can just say p plus move, and that should do the same result. That should give you the same result. But translates start to make sense when you have a lot of other transform being combined to it. So for now, if you're just having a move value, it might be okay to just use addition for the vectors. But when you are having multiple transformation matrix, then using matrix value, matrix multiplication with the vector start to make sense. Okay. Now let's look at the other transformation. In this case, a scaling. Now what you want to do, if you have a geometry like this, what you want to do is to scale with certain size or certain scale value for x, y, and z value for each coordinate. So let's say if this point position is x, y, z, and the scale value is, let's say, a, b, c. Then the new coordinate is ax, by, and cz, which is equivalent to the multiplication between the p and the s value here. So for the scaling as well, it's pretty easy to do it within the vector calculations, which is the multiplication between the vector and vector, which will create a multiplication and as a result a scaling transformation for each coordinate. So pretty similar to translation. If you are just having a scale transformation, it might not be a good idea to use matrix, but instead just multiplying two vectors together just makes sense to do the scaling transformation. But same as the transformation, if you want to combine multiple transformation together, using matrix start to make sense. So let me show you how this how it looks like for the scaling transformation in a 4x4 matrix. Now 4x4 matrix is used to do the 3D scaling, and which is similar to translation, and you have x, y, z1 for the left hand side vectors, which in Houdini you just need to declare those three values, x, y, z. And for the scaling, if you have a scale value a, b, c, it actually looks like this: a, b, c on diagonal, and the last one is 1 and other value is 0. And this is the form for the matrix for the scaling. And if you try to calculate this one, it looks like a multiplied by x, and for the other one it's all 0, and for the second one b multiplied by y, and for the other value is 0, and for the third one it's c multiplied by c, and for the other one is 0, and the last one is 1. So the result for this vector is same as the one that has been multiplied between two vectors. So this is how a scale matrix works. And as you can see, it is using the different position in the matrix in order to use the scale, and between the translation. The translation was using this one in order to translate. So each of the part in matrix has some meanings in terms of a transformation. Now let's try to see this in Houdini, see how we can write this in a VEX code. Okay, so first of all, I am going to copy this sphere and going to create a point wrangle. Okay, and for this one, I'm going to name it as scale. Okay, and first of all, let's create a scale vector. Let's say with the CHB so that we can declare as a parameter. Okay, let's start with by from 1, 1, 1, which is going to be the basic scale. Okay, now for the scale functions as well, we need to declare the identity matrix first. So let's see what scale function looks like in a VEX function page. And if you go to the scale, you have 3 types of parameter options, and the basic one will be, I think, this one. The first one is the output parameter, which can update the input, so the matrix value it is. And the second parameter is the vector that you want to use for the scaling. And I think the vector 3 is the basic parameter we could use. So I guess we could use this parameter. Now, let's start by creating an identity matrix using ident function, and then use scale function to scale this matrix with this scale vector value. Okay, now I could try to update this position coordinate by multiplying the matrix that I have updated. Now currently the scale value is 1, 1, 1, so it doesn't change, but if I try to increase this one, you start to see the scaling for x, y, and z coordinate. Okay, so seems to work just fine. And this still works even if you try to multiply this scale vector directly to the point position. It still do the same stuff. So most of the case, if you're just having the scale transformation, it might be a good idea to just use the vector transformation or vector multiplication between two vectors, the position and the scale. But as I said, the matrix also is useful when you have a more complex, more compounded transformation. So this is how you can use matrix to scale the point position or geometry. Now the last basic transformation I want to show you is the rotation, and this is when the using matrix seems to make a lot more sense other than the scaling or translation. Now we have already seen how we can do the rotation using quaternion, but you can also do the same rotation using matrix as well. And the good thing about matrix that you can combine with a translation and scale at the same time to do the transformation in one process with just one matrix. Now the expression for the rotation in matrix is a bit too complex to show in Sketch, so I'm gonna show you the basic example using 2x2 matrix, which can be used to do the 2D rotation. So 2D 2x2 matrix looks like this, and for each one, when you want to rotate the coordinate by theta, it looks like this: cosine theta, sine theta, minus sine theta, and cosine theta. Now if you draw this on a graph, it looks like this. Let's say this is theta, and the coordinate right here is cosine theta and sine theta, and let's say the size of this one is equal to 1. And for the second row, which is can be from 90 degrees, you create a theta again, rotate theta again, and then for this part is going to be the minus sine theta and cosine theta. Okay, if you remember the trigonometry. So the first row corresponds to this point, and the second row corresponds to this point here, coordinate here. Now if you try to multiply this 2x2 matrix with the vector to vector 2, in this case, so x, y, from the right hand side, what you get as a result is x cosine theta minus y sine theta for the new x value, and for the y value, x sine theta plus y cosine theta. And this is actually showing the rotation, and you can check that by applying x and y value with a value something is on the axis. So let's say there's a x value here, which is, let's say, 1, 0. So if you input this x, y value, when the x is equal to 1 and y equal to 0, then as a result, you get a x is 1, so cosine theta is the x value, and for the y value, you get a sine theta. And that is actually equivalent to this value here, so which is equivalent to this point being rotated by theta. Okay, so let's see, let's think about the points here next. So that is going to be 0, 1. And if you input this 0, 1 to this calculation, this one will be minus sine theta for the second one, and for this for the y, this will be cosine theta, and which is equivalent to this one again, which means this point has been rotated by theta, and to create this coordinate. So this is the matrix, the rotational matrix for 2D space. When it comes to 3D rotation, you need to specify an axis with a rotational angle theta, and it will give you a much more complex matrix. And if you just need a rotational matrix, you can express it by 3 by 3, and which consists a lot of sine and cosine trigonometry values for each of the values, which I'm not going to write it here. You can check that out in Wikipedia or any other page where it explains the detail about the matrix rotation. But for now, remember that the rotational matrix can be expressed in a 3 by 3 matrix. And it can also be expressed using 4 by 4 matrix. The 4 by 4 matrix itself can use the 3 by 3 part on the left top corner, and this part can be used for the translation, and this part can be used for the scaling. So a combination of these 3 values will create a complex matrix values. But the things that you need to remember, that basically the rotational matrix can be expressed by 3 by 3 if you just want that as an only value, only transformation matrix to use. But most of the case in Houdini, I will recommend you to use 4 by 4 matrix to create a rotational matrix, since it can be extended. It can be extended by combining with other transformation matrix. Now let's try to use this rotational matrix in Houdini, and let's see how we can use this. So I am going to use this time cube to rotate, and I am going to create a axis as so that it's visually obvious which axis I'm using to rotate. So I'm going to also create a line with some random direction, which is going to be the axis for the rotation. Okay, yes. Now let's create the point wrangle to rotate this box point coordinate. So I have right now 8 points. So for each point I would like to apply a rotational matrix transformation, and I'm going to use this line as a guide to get the axis direction. Let's name this rotate. Now first of all, let's get the axis value, shall we? So to do that, first I'm going to create a variable called axis, and then axis to the point position from the second input for capital P, which is the point position, and the since the point is line is created by 2 points, and I'm going to get the second point so that it will also declare the direction from the center of the space, which is 0, 0, 0 in this case. Now after I get the position, I'm going to normalize this to make the size of the vector to 1. Okay, now let's also create some parameters for the angle, how much I want to rotate, and it has to be in radians, so let's give a radians function first, and inside let's create a parameter called angle. Let's promote it, and let's give the range for this angle value from 0 to 360, which I'm going to use it as a degree value, and then convert it into radians inside the code. Now we are ready with the data. Now it's time to create a rotational matrix. Now, as always, we will start by creating an identity matrix. Now let's go back to the VEX function page and see the rotation function. Rotation or rotate. Rotate. And there's a function right here. And this rotate is used to rotate the matrix with an amount of angle together with the axis. There is other options here, but I'm going to use this parameters here. So the matrix is the first parameter, second one is the angle in radians, and then the axis for the rotation. Now let's use the rotate to rotate this matrix. The amount is angle and the axis is axis. Now that I have updated the matrix, I can now use the point multiplication with the matrix that I have created. Okay, now let's also show up the line where the axis is by using merge with the rotated box with the line, so that it's clear which axis I'm using for the rotation. Now it's time to change the sliders to see the geometry is actually being rotated or not. And based on this axis direction, I think the box is rotated as I wanted. Now let's change the axis direction. Let's say 0, 1, 0. Now in this case, the rotation should be done like this, using a y-axis. If the axis line is 1, 0, 0, then the rotation happens like this. So it seems to work just fine, and it is one of the most used functions, which I'm talking about, this rotate function, in order to rotate the object inside of VEX, together with the qrotate from using quaternion to rotate the object. Now that we have done a basic transformation, a single transformation for rotation, translation, and scaling, it's time to test out the combination of these three transformations to do more complex one. So let's try to create a simple situations where you want to scale the geometry and translate the geometry and then rotate the geometry. And let's also see the difference by changing the order of these transformation. I'm going to use the cube as a simple example to transform the object. Okay, now I am going to create a point wrangle. And let's name this combine matrix. Okay, now inside the code, I'm going to first start by creating a identity matrix, like I always do when we start doing the matrix transformation. So matrix mat is equal to ident. Now let's start by creating a necessary information like an angle or axis, or moving translation values or scaling values and so on. So first of all, angle, I'm going to do the similar things that I did previously. So radians and CHF angle, and axis, which is the vector value. I'm going to make it simple for the axis. I'm going to make it as a y-axis. Okay, and for the movement, I'm going to create a vector, but not all the parameters going to be parameterized, but only the x value is going to be parameterized with the CHF, so the float value. I can only change the float value for the x value for the translation, and for the scaling, same for the translation. I'm only going to change the x value for the scale. For the other one, let's keep it 1. Now let's promote. And let's also set the range for each of the parameters. For the angle, from 0 to 360 degrees. And for the move, 0 to say 2. And for the scale, 1 to 3. Maybe move to 0 to 3 as well. Okay. Now let's try to create 3 transformations out of these information. First of all, scale. So scale, I'm going to update matrix and use scale to update the material. Now next I'm going to use rotate and use mat to update the matrix, and angle with axis, and last of all I'm going to use translate mat a move. Now that I have 3 transformation applied one by one, this is also equivalent to multiplying the different matrix one by one. So by using scale, I have just multiplied this identity matrix by the scaling matrix, and after doing this, by using rotate function, what I have just done is to multiply the result of this one with the rotation matrix created by this angle and axis information. And then last things that I'm doing is to multiply again the new matrix, which is the translation matrix given by this move vector, with the last one. So as a result, what you get is the combined transformation matrix. And by using this to multiply with the position vector, you can apply all these transformation. Now I am having a flat plane here. That is because I have scale 1 here. So let's set it to 1 for the scale as a starting point, and let's start by changing the scale value, since this is the first value that I'm doing, first transformation that I'm doing here. So if I change scale, it looks like this as expected. And if the next one is the rotate, so if I do the rotate, it rotate in the same position from using the center position like this. And now the last thing is this move, which moves the box into a x direction, which is also expected. Now let's give this back to the original, and let's see if I change the order of this transformation and see what happens. So let's say if I move this translate to the first and see what happens. So in this case, the move happens first, then scale. Now you can see that the scale is always happen from the center of the space, so 0, 0, 0. So the box is scaling, but at the same time the position is also changing. And if I do the angle, if I do the rotation is also based on the 0, 0, 0 position as a pivot. And so as a result, you get this kind of big rounding rotation. So just by changing the order of this matrix transformation, what you get as a result is totally different if you multiply different matrices. Now if you have this 3 transformation, the total number of variation you could think of is 6. So scale, rotation, translation, scale, translation, rotation, rotation, scale, translate, rotation, translation, scale, and so on. And there's actually a constant value for it to determine the order inside the VEX code called math.h, which you can check by going into this file here, which is included in the installation of Houdini, which we've seen it before in the quaternion session. And inside here, there's some constant value, and this is the one that I have been talking about, which declares the order of the transformation. So the first one says scale, rotate, translate, and the second one is scale, translate, rotate, and so on. Now in here you don't really use that, but there is some functions which asks you to enter this value. Now next thing that I'm going to do is to use that function. Now since I'm going to do the similar process with different function, I'm going to duplicate this whole stuff and try to change this. I'm going to name this maketransform. Okay, and I'm going to delete all these matrix transformation function and left with those basic information right here. Now what I'm going to use is the function called maketransform. Let's see what it does by going into the VEX function page. Maketransform. If you look at it, you see that this maketransform can be used to combine the translation value, the rotation value, and the scale value. And if you want, you can additionally set the pivot or a pivot rotation as well, and also a shears. Now I think using this one is the most basic way, basic stuff we want to try out in this case. So in this case, we first need to set the parameter for TRS, which determines the order of the transformation. Either translate comes first, or rotation comes first, or scale comes first, and what comes next, and so on. And for the second parameter, this is the value which we have also used last time with the quaternion to determine which rotation comes first. Since the rotation is in vector, we have to declare it in a Euler angle, x, y, z. The angle for the x-axis, y-axis, and z-axis. And all of those information can be seen from this math.h at this file directory. Now we can check this by copying the directory value here, and then go to the window and open up hscript text port and paste the directory that I've just copied. It gives you a folder which where we have this directly right here. So I'm using Macintosh, so it shows the directly like this, but if you're using Windows, you should be able to see some different directory. Now in Mac, I can use the go-to folder to check the file, and inside of the folder there should be a file called math.h. So let's open this up, and this is what I see inside. And there's two constant values which I can use for the TRS, which was the order for the transformation, which is this one from 0 to 5, and the XYZ rotation order, which is also from 0 to 5. Okay, now I am just going to try to choose one of the values, and since this is from 0 to 5 for all of them, maybe I could have the sliders for those two values from 0 to 5 in Houdini. Now let's go back and let's remove this one. So we had TRS and XYZ for the parameters, and for the other T, R, and S will going to be the vector value in order to transform. And if you look here as well, unlike most VEX function, this function expects rotation in degrees, not radians. Now some of the functions in VEX use degrees like this one, so be careful about it. Which in this case is R value. The rotation value in Euler, XYZ value should be in degrees. So consider that. Let's try to create some functions. Now, so as it says, the angle should be in degrees, so we should first remove this radians function so that we can directly use this value as a degrees. We also need to make it as a vector for the rotation, so without using this axis. So let's do that by creating a different vector called rot set 0 ang 0. Okay, now that we have three values for the rotation, translation, and scaling, and we could also have two parameters for TRS to determine the order of the transformation. Let's set it as integer value, and XYZ to determine the order for the XYZ rotation. Let's promote it, and for these two values the range is between 0 to 5. Okay, now let's start with 0 and call the maketransform function. Now the first value was TRS. Okay, so TRS and XYZ, and then the translation vector, rotation vector, and scaling vector. So translation vector is move, the rotation is rot, and scaling is scale. Okay, and as an output you get a matrix. So in this case you don't need to create a identity matrix, but this function itself will create a combined matrix, transform matrix. So I don't need this identity anymore, but instead I can directly create a matrix out of this maketransform. Okay, as a result, this will can be used to modify the coordinate of the box right here. Now let's try to reset it to simple the base stuff. Now since when the TRS is equal to 0, which is equivalent to the scale, rotate, translate order. So first the scale happens like this, And for the second one, the rotation happens, so this one happens. Then the translate happens. So it seems it's working. Now if I change the TRS to 1, something different happens. So let's go back and see what's the order. So that's the order. Starts from the scale and then translate, then rotate. So scale happens, then translate, then rotate. So it seems like it does what it does. And if I same for other one, by changing the order you change the how the translation works. And since there's only one angle, this doesn't really change anything because I only have y-axis angle. But you see what kind of difference you get with the different angles, since we already saw it in a quaternion sessions. So I'm gonna skip about this one. Now this function is pretty handy when you have when you want to create a combined transformation in one matrix. Things you need to be careful of is the order of the transformation, which transformation comes first and which comes next. Now the next thing I would like to show you is some useful function you can find in VEX in order to deconstruct the matrix that you have created. Meaning, let's say you have created the matrix using maketransform, and maybe after you have created, you might want to like break it or crack it into a different element back again into like something like translation vectors, rotation vectors, and scaling vectors. And you can actually do that with a function called cracktransform. Then I'm going to show you how you can do that. To use that cracktransform, I'm going to first store this matrix into a attribute to test out. Okay, so I'm going to create a for@mat and store this matrix that I've created into this attribute. So if I go to each of the point attribute, there's this mat attribute. The 4x4 matrix values apply for each of the point. Now let's create another point wrangle connected to this maketransform, and let's name this cracktransform. If you go to the VEX function page for the cracktransform, it shows you what you can do with it, and there are several stuffs you can use. One is to export this specific type of transformation, but what I would like to use this time is something, maybe this one or this one, to extract a translate, rotation, and scale vectors. Now this one seems to export more information, but need to provide a pivot rotate as well as an additional parameter to get the shears, since I don't need the shears, I think, so for now. So I'm going to use this parameter set. So what I need to set is the TRS XYZ, which is similar to maketransform. So I need to specify the order of the translation when we have created the matrix. Okay, so it has to be the same value as the one that I have set previously when we did the maketransform function. And then the pivot. Now if you did, now I didn't set the pivot for the last one, so normally it should be in a 0, 0, 0 position if you haven't specified by yourself. So I think this is going to be 0, 0, 0 for now. And X form, this is the matrix that you want to crack from or deconstruct from. And as a result, as an output parameter, you get a translation vector, rotation vector, and a scale vector. Okay, now I am not sure if the deconstructed value is going to be radians or not. Maybe it says rotation angles are returned in degrees, whereas many of the VEX function you can use. So I guess that by using this function, same for the maketransform, the radius, or I mean the angle that is going to be retrieved is going to be in degrees. So let's check that out as well. So let's try to use this parameter set, shall we? Now, in order to use that, we need to know the value for the TRS value and XYZ value as well. So let's give a TRS parameter. Now let's link it with the previous one. Okay. Now let's go back here and copy this parameter and paste it right here using paste relative reference. Same for the XYZ value. Copy this one and paste it right here. Now let's make sure this is linked. Okay, now I am going to use the cracktransform. Now the first parameter is TRS, second one is XYZ. Now the third one was the pivot, which could be 0, 0, 0. And for the first one, which is going to be the matrix, and I have stored the matrix value inside the attribute called mat. So this is the one that I'm going to deconstruct, and I need to output the parameter. I put the vector parameter to tr and s. Now I don't have these tr and s yet, so let's create that as well as an empty vector. So tr s. Alright, now let's have all these values being applied to the attribute by creating a t for the t, r for the r, and s for the s. Okay, now let's go see the geometry spreadsheet for the point, and let's first look at the t value, which is set as 1.4660, and the last one is pretty much close to 0. Now let's go back to the maketransform and see what was the value for the translation, the move value. So that was 1.466 for the x value, so which is equal to the one that I've got here. Okay, for the scale, it was 1.347, which I've got from the cracktransform. And if I go back here, the scale is the same value, 1.347. Same value here. Okay, which looks good. Now for the translation, I mean for the rotation, which is 0 minus 259.70, which is equivalent to 259.7 plus 360 degrees, which is equivalent to this one. So, which is equal as well. So, as you can see, by using cracktransform, you can get those translation, rotation, and scaling value, which sometimes is pretty useful after you have created the matrix. But one thing you have to be careful is that if you want to crack the transformation, you always have to know in what order the transformation has been done for the first and second parameter. Also the rotation order as well. So if you don't know about that, then it's not possible to crack the transformation. So remember that. Now that I have shown you the basics of transformation using matrix and also shown you how you can combine the matrix together to create a more complex transformation, what I'm going to show you is to use this information to make some interesting transformation as an exercise. So let's try. So first of all, I'm going to try to start with the box. And let's set the size as the default value here. Now, and I am going to create a point wrangle. Now let's think about what kind of transformation that I would like to try out here. Let's see, what I want to try out here, first of all, as an exercise, is to use all translation, scale, and rotation. And maybe I can combine with some animated rotation angle or something to make it a bit more interesting, like motion graphic style geometry. So let's see. So first of all, I'm going to start by creating a matrix using ident. Okay, now let's see, I would like to rotate the box like in circle using some radius. So to do that, I think first of all I might need to translate the box into something like X direction. Then do the rotation using Z-axis. And maybe based on the position of the box, I might want to change the scale of the box as well. So let's try to see how we can do that. Now I'm going to start by setting some parameters like the radius. Let's name this rad as a parameter, and also a angle to rotate. I'm gonna change these to radians. So now I have two parameters. One is the radius, one is the angle. Let's set the range for these one. The radius, I'm going to set the range from 0 to 5. For the angle, 0 to 360 degrees. Okay, now let's first of all translate this matrix so that I can create a translation matrix to move the geometry to X direction. So mat set to a 0 or rad 0 0. Okay, and let's see the result by multiplying the point position, each of the point position of the box with the matrix. Okay, now I can change the radius and see if the box is moving to X direction. I think it does. Now next thing I would like to do is to rotate this box using Z-axis so that it rotates like a circle. So after I have translated, I'm going to create the rotate function to update the matrix with the angle with the axis 0, 0, 1, which is the Z-axis. Now if I change this angle, yeah, it is rotating as I expected. That looks good. Now next thing I would like to do is to change the height of the box based on the position or based on the angle. Maybe what I would like to create as an effect is when the angle is the multiplication of 90 degrees, I want to make the height of the box really high, like 3 times higher than the current height. And so let's say the height for the box is 3 in this position, and until 45 it gets smaller and becomes 1, and after this, going back again to 3 and 90 degrees and do a wavy scaling from 0 to 360 degrees. So to do that, I think I can use some trigonometry functions based on the angle as well. So from 0 to 90 degrees, I would like to have a value going from 1, 0, 1, or 1, minus 1, 1. So I can consider this range as a let's say 0 to 360 degrees for the cosine value. So when the angle is 0, the cosine will give you 1, and when it's 180 degrees, you'll be able to get minus 1, and if it's 360 degrees, you get 1 again. So out of this current angle, to make 0, 90 range to 0, 360 degrees, you just have to multiply by 4. So ang multiply by 4 and use this with cosine should be able to give you a value in between minus 1 to 1. Okay, so let's make this name as size. Now I don't want to use a negative value for the size, so after I have got the value in between minus 1 to 1, I'm going to use fit function to remap the value from minus 1 to 1 to 1.0 to 3.0. Okay, and this is going to be the new size for the box. Now next thing I can do is to do some scaling at some order. Now maybe I can scale the geometry first, then translate to x direction and rotate. So I can give the scale right here, scale mat set a 1 size, or maybe we're moving to the x direction, so size 1, 1 might make sense. Okay, so if the angle is 0 and if the radius is, let's say, 2, at the angle 0 the size is 3, and when it gets to 45 it gets 1. If it's get to 90 degrees it gets 3 again, and 1, 3, 1, 3, 1, 3, and so on. And if I don't want to make the scale happens from the center of this box, which happens is because currently the scale activates first, and currently the scale pivot is placed on a 0, 0, 0. So when we do the scaling, the box will always be scaled from the center. If you don't want to do that, then what you can do is to add another translate before to move the box in x direction. In this case, mat set original box size was 1, so if you want, you can just move by half size but to the x direction, like 0.500, and as a result the pivot becomes on the bottom of the box, and as a result you'll be able to have this box rotated so the bottom always stayed on the circle. Okay, now that looks good. Now we can make animation by setting some expressions to use the frame related data. So the current frame divided by the end of the frame, which is going to give you the value in between 0 to 1, and multiply by 360 will give you a looped angle from 0 to 360 degrees. We'll create animation like this. Okay, which was a really simple exercise for using a transformation for the rotate, translate, and scale. Now, using the same transformation, let's try to do some more complex transformation, a bit more interesting one. Okay, so I'm going to start by creating the box again, but this time I would like to create a lot of points to this box. Also, I set some size to this one. So first of all, I'm going to set the size for the Y to 5. Okay, and for the X, I am also going to change this to a polygon mesh. And then change the axis division for X, Y, and Z to 5, 50, 5, so that you have a bunch of points for this box. And I would like to control each of the point using transformation. And this time for each point I would like to apply a different kind of values, different kind of matrix values. Previously I was using the same matrix transformation for all the points, but in this time I would like to try to apply a different types of transformation for each of the point based on the point position. Now let's see. What I would like to do is to try to create some transformation like twisting and bending using this 3 basic transform: rotation, scale, and translate. Okay, so use point wrangle, connect it with this one, and let's name this twist and bend. Okay. Now, first of all, I would like to have some information about this box height. So let's create a parameter called box height, which has already been defined by 5. Really? Now, let's also create some parameters that I want to control by myself. First of all, the total twisted angle. So float twist ang, and this time I'm going to use the float value and I'm going to make it as a radians, and or maybe the value in between 0 to some values multiplied by pi instead of making this as a degrees. Okay, so by having this, this is going to be the range or the ratio of the angle. If it's 0, it's the 0 degrees. If it's 1, it's 1 multiplied by pi, so that's equivalent to 180 degrees. Now let's go and let's set the twist angle maximum to 6, and for the box height I can copy this value here and paste it right here so that it's going to be linked. Now let's also add some other values. What I would like to do next is to do the bending simulations, or bending for deformation or transformation, and in order to do the bend I need to set some pivot location for this box. Now I could set a pivot location somewhere on, offset it on X direction or Y direction or Z direction. So I would like to create some parameters for the offset value to define the pivot. Okay, so float bend rad chf bend rad. Okay, and also for the bend angle as well, so bend ang is equal to bend ang multiplied by pi for this as well. Okay, now For the bend angle, I'm going to keep this as from 0 to 1, or maybe 0 to 2, since the 0 to 2 means 0 to 360 degrees. And for the bend radius, I'm going to set the range between 0 to 5. Alright. Now, I think I have all the necessary information to do the transformation. Now let's try to create the matrix to do the twisting and bending. So first of all, first thing first, I'm going to create a identity matrix. All right. Now, next thing I'd like to do is to try to calculate the angle for each of the point for the twisting. Okay, based on the height of each point in y direction. So first of all, let's get the height position, which is at p point y, and I know that it is range in between the minus 0.5 box height to a 0.5 box height. So I can use the fit to remap this point height from box height multiplied by 0.5 to box height multiplied by 0.5, and as a range I'm going to set as 0 to this twist angle that I have declared, like this. So at each of the points should have a different values, and that is between 0 to twist angle. Okay, so I'm going to name this variable as t_ang, name as a twisted angle. Now let's call a rotate function to rotate this matrix. So rotate this matrix with the angle that I have just created with some axis. In this case, I'm going to set the y axis as the rotation axis. So set 0, 1, 0. Okay, now I think I have some spell mistake here. Just have to be box height. Okay, now let's try this transformation first by multiplying this matrix that I've created with the point position. Now currently I'm only using this twist angle, so if I do it, I can see that it's already twisting the box by a maximum angle that I have declared here. That's good. Okay. Now next thing I would like to do is to make this overall shape like a cone-like shape or a rice-like shape. So making the tip of the box smaller and make it like an arc as a section. So let's try to do this after the twisting, somewhere around here. So for the scaling value, it should also be related to the height information. So maybe I can first copy this one and then name this to scale, and until here that's fine. And for this one, since I would like to create like an arc-like shape, it might be a good idea to use a trigonometry here as well. And a value, so this is the minimum height and this is the maximum height. And for the minimum and maximum height position, I would like to set the scale to close to 0. And if it's on the middle, I would like to set the scale to 1. So I think I can use this sine function to do that together with the 0 to pi angle. So let's change this twist angle to pi and use this fit remapped value with the sine function, and as a result you should be able to get the value in between 0 to 1. Now I would like to set the minimum for the scale to be a bit larger than 0. So I'm also going to use the max function so that the 0.01 will be the smallest value here. Okay, now that I have this scale value based on the height of the point, I'm going to use the scale function to update the material. I mean the matrix using this scale value. So in this case, I don't want to scale in y direction, but only on x and z. So scale for the x, 1 for the y, and scale for the z. Okay, now as a result, I have just got this cone-like shape. Okay, that looks good. Now, what I want to try out next is the bending deformation, which I think I need another rotation. But I also need to do the translation as well in order to set the pivot for the bending. Now the pivot direction is already being declared using this parameter. So let's first try to move this whole geometry to specific direction. I'm going to move this into a minus x direction using a translate mat set minus a bend rad 0 0. Okay, and if I change this value here, whole geometry is moving to the negative x direction like this. Now that the pivot has been gone a bit far from the center, I mean the pivot always be the center in the space. So whenever you rotate, you use this center position as for the rotation pivot. So as a result, if you rotate using a z-axis, you should be able to bend this geometry. Now in order to bend it, you also need to think about you also need to declare the different angle for each of the point. If you just use the same angle value for the rotation for all the points here, then you're just rotating the whole geometry. But in order to do the bending, you need to set a different rotation angle value for each of the point. In this case, I guess, again, based on the height of the point. So let's try to do that. Let's first create a bending angle, which can be copied from this one and change this twist angle to the bend angle. Okay. Now that I have this angle, let's create a rotation matrix, or combine a rotation matrix to the current matrix using the negative bang, and then let's use the z-axis, so set 0 0 1. Okay, now if I change this one, you see that the geometry starts to bend from the 0 0 position, the bottom position. Okay, that looks good. So I now have in total 4 transformation. First, the twisting rotation. Second, the bending radius, or maybe the scale, which is based on the, which is to declare the cone shape. And then the bending radius, then the bending angle. Okay, now let's also try to make this as an animation as well to make it a bit more interesting. Okay, so let's first think about rotating this whole geometry like 360 degrees by a frame, using from first frame to end frame, continuously rotate. Now to do that, the rotation can be controlled, this z-axis rotation is controlled using this final rotation matrix transformation. Now currently I'm only using this angle, which is declared by setting a different values for each of the point, but by adding additional angle to this one based on the frame, like current frame divided by f end, and maybe multiply this by pi multiplied by 2, you'll be able to rotate the whole geometry 360 degrees like this. Now it still might not be that interesting because it looks really static currently. So maybe if I could rotate this twisting as well as an animation, that could be more interesting. So let's try that out as well. So to do that, we could try to add the frame-based rotation to this tank, just like we did for this bending angle. So for the twisting angle, I'm going to add the pi multiplied by plus equal pi multiplied by 2 multiplied by a frame divided by f end. Now slowly something has happened, but it's still hard to see what's happening. So let's try to multiply this by integer to give more rotation for this twisting. So t mult, let's name this t ang mult. Okay, and if I raise this up, I start to see more interesting things going on. So the twisting is rotating faster than the whole rotation and gives you a bit more like a creature-like shape movement. Okay, let's also hide the edges, and looks pretty interesting now. Okay. Yep. Okay, so by understanding the simple concept of the matrix transformation, you'll be able to create this kind of interesting transformation pretty easily, and that's pretty straightforward as well. Now I want to show you one more thing for this exercise, that is, after I have created this complex matrix to create this kind of shape, you can actually reverse engineer this matrix to make this geometry go back to the original shape, which is this box. And in order to do that, you need to do a reverse matrix transformation. So from the current point position, which is this one, you need to do exactly the inverse matrix transformation. And the easiest way to do this is actually to create a inverse matrix of this final matrix and multiply it with the current point position, the updated point position, and as a result you'll be able to get the original geometry, which is equivalent to matrix multiplied by the inverse of matrix become identity, and identity means that the current position multiplied by identity will just give you the original point position. So I think it makes sense. By using inverse matrix, you'll be able to get the original point position. So let's try to see that. First of all, I'm going to store this matrix that I've created as a matrix to the attribute, to point attribute, like this. And then create a point wrangle, another point wrangle. And let's name this reset mat or inverse mat. Now let's get this matrix that I have stored in an attribute, which is for @mat. Now, in order to create the inverse matrix, let's name this imat, is use this inverse for the mat, invert for the mat. Now, as I said, by multiplying this mat by invert mat, you'll be able to get that identity. And actually, the current point position has already been multiplied by this matrix. So if I multiply this with invert matrix, this one and this one will give you an identity matrix, and an identity matrix multiplied by a point vector point position will give you just the same point position, which is going to be the original point position. So as a result, if I multiply this updated or modified point coordinate with the imat, you'll be able to get the original box like this, which, if you understand the matrix, how the matrix calculation works, I think this makes sense. Now these are the basics how you can use matrix for the transformation in Houdini using VEX functions like rotation, translation, and scaling, which was pretty straightforward, I think. Now, and the last, I would like to show you some of the functions which output the matrix value for some additional transformation, which could be really useful to use with. So I'm gonna show you them with some examples. The first function I want to show you is dihedral, which I have already shown you in the last session for the quaternion. Quaternion, using dihedral functions, you can output the quaternion value or either a matrix 3 value for the rotation. And the dihedral was used to change the direction from one vector to another vector direction. And it can also output the matrix C3 values for the transformation. So let's see how it can be used with the matrix. Okay, so I'm going to first create the two lines and change the direction for each of the lines with different value. I'm going to just set some random values for two lines here. Okay, let me set it to some different values here. Now, okay, now I'm going to set some different colors for each of the lines. For the first one, let's say I'm going to set the blue. Okay, for the second line, I'm going to set it as red color. Right. Now, for the first line, I'm going to create a pipe geometry, which I'm going to translate or transform using dihedral. So, polytube or polywire with this line. And let's set the division to some values and keep it as it is. Okay, now I am going to create the point wrangle to, first of all, to deform the geometry that I would like to transform into the first input. And for the second and third, I'm going to input this axis lines. use it for to retrieve the information for the direction of the curve, the direction of this line. Now let's name this dihedral. Okay, now let's write a code which is pretty similar to what we did last time. So first of all, we are going to retrieve the vector value, a vector directional value from the line, two of the lines. So let's create a vector. First vector will be cdir, and get the point position from the second input from a p attribute for the second point. And let's normalize this to make it as a unit vector. Okay, for the target direction, I'm going to do this pretty much the same things for the input 3, which is the third input, and the rest of the stuff is pretty much the same. Now that I have two vectors, one for the blue one for the red one, what I want to do is to move this geometry, orient this geometry to align with the red one, which is currently with the poly tube or poly wire is aligned with the blue one currently. Okay, now to do that, we can use this dihedral function and input two vectors like this, and as a result what you get is a matrix 3. Now last time we have used this dihedral to create a quaternion, but you can also actually create a matrix as well. So this time I'm going to try to use this one. So matrix 3 mat is equal to dihedral cdir tdir. And if you try to multiply this point position with this mat, it will just rotate the tube to this red line here. Now let's check these out all together by merging the blue and red line all together with the geometry. Now currently the geometry used to come here, but by using the dihedral I'll be able to move the points to the red direction. If I change the direction of the red, the dihedral will just create a correspondent orientation matrix to rotate the tube. Okay, that was straightforward. The next function that I want to show you is called lookat, which is used to compute a rotation matrix or angles to orient the negative z-axis along the vector to form under the transformation. So it can be used to create a lookat orientation transform matrix, either using 3 of those parameter sets to do some transformation. So let's try to see how we can use this with an example. Okay, so first of all, I'm going to create some cone-like shape. Okay, so I'm going to start by creating a circle. Let's set it to polygon. And let's set the divisions to something like 4. Okay, and then let's also set the, let's also move this to negative z direction, since it says the lookat function works along with the negative z-axis. Okay, so let's create the tip point of this cone on a negative z direction by moving this circle or square to negative z, maybe -2 and z direction, negative z direction. Then let's also make this geometry scaled a bit smaller, like 0.1. Okay, now I'm going to merge these two together, like this, and create a lofted geometry using polyloft to create like a cone-like shape. Now I might need to close the face here by setting UWrap to on, and maybe I can set the scale to 0 so that it will be really like a cone. Okay, looks fine. Now I can try to use the function lookat. Now in order to use the lookat, I need to set two vector information. One is the from vector and one is the to vectors. Now the from vectors could be from the center, which in this case is 0, 0, 0 position. So I just need one more vector, which is a to vector. So let's create a add node to create a point with your own customizable point position. So something like this. And let's use this point to be the to position, to direction. Now let's create a pointer angle and connect the lofted geometry as the one that I want to deform, a transform, and this add node to the second input. Okay, and let's name this lookat. Okay, now first of all, I'm going to create two vectors. One is from, one is to. Now the from vector, I'll set it as 0, 0, 0 for this case. And for the two vectors, I'm going to retrieve the point position from the second input, which is this one. So point second input p 0. Okay, now that I have two vectors to create to use the lookat transform, I can go back to see what kind of parameters that I could use. This could be the simplest parameters, only using two parameters from and to. Another one is using a roll value, which is the equivalent to the rotational values, and also a up vector, which is to define the up vector or for the orientation of this cone. Okay, so maybe we could try either one of it to see what the third parameter does. Okay, maybe using the second one is easier, so let's try to use this one. Now it doesn't really say what this angle is, if it's either radians or degrees, so let's try to use radians first, if it still works. Okay, so let's use the function lookat, which output the matrix 3. So matrix 3 mat is equal to lookat from, to, and some roll angle, and let's create the roll angle using a channel value or parameter value. Alright, now let's try to make this as a radians and set the roll value in between 0 to 360 degrees. Oops. Okay, and finally I'm going to multiply the matrix with the vector point position to actually transform. Okay, now I have successfully moved or rotated this cone, which was facing -z, to the point direction that I have specified by myself. And if I move this point and change the direction, the direction of this cone facing is following this point direction. Looks good. Now that looks good for the overall the main look at transformation. Let's also try to change the roll angle here. If I do it from 0 to 360 degrees, you can see that I do see that the angle is changing a little bit, but not that much. Meaning this might not be in radians, but this might have to be in degrees. So let's change this to just the original roll without using radians and set it as degrees, and looks like it works now. So this roll angle seems to work to rotate the oriented geometry using this look at direction as in a rotation axis, and rotates the geometry like this. Okay, that looks good. So this function is also pretty useful when you want to make this geometry facing to specific direction using matrix. The last useful function in order to output the matrix that I want to show you is called instance. If you go to instance function page, it says creates an instance transformation matrix, and it also says creates a transform matrix from the given arguments using the same method that the copy SOP uses to transform its output instances. So just like copy SOP, it can change the position of the geometry as well as the orientation and the scale using all these parameters, so which is pretty convenient to use, and it directly output the matrix. So it's pretty useful when you want to directly change the position, scale, and rotation based on some information you already have, not with the angle like scale value or translation value, but a bit more direct value, like where you want to position the geometry, where it should be faced, and so on. Just like you using copy SOP node. So what I'm going to try to do this right now is to try to mimic the behavior of the copy to SOP node with this function as an example. Okay, so let's see. First of all, I am going to create a similar geometry that I have created previously, I mean the cone geometry. So I'm going to copy the one that's from here to create the cone, just this one. Okay, now, and I am also going to create a bunch of points from a sphere. So I'm going to create a sphere, and let's set it as a polygon and set the uniform scale to 3. Okay, and also create a normal direction to each of the point using normal node for the point, so that I have a bunch of normal direction on each point. Okay, now if you use a copy to SOP node, let's say like something like copy to points, for this geometry to place on top of this sphere, it looks like this. Now it seems like the copy to SOP nodes works on positive z direction, so let's change the order of this one to be, let's give this to +2, and also make this different so that the backside will be flipped. Okay. Now, if you use copy to subnode, it looks like this. And I would like to recreate or reproduce this kind of things, a kind of output using the VEX code, in this case, a instant function. Okay, now, first of all, in this case, one geometry is copied to a several point position on the sphere. So to do it simply, I'm going to start by using a for loop for each loop, and I'm going to use this for each point. So each point I'm going to create a loop from this sphere. Okay. So each point inside this loop, each point is accessed, and each point is the position where I want to copy this geometry. Now let's create a point wrangle and connect this polygon that I want to deform or move to the first input, and give this point as a guide to the second input, and connect the last one to the end node. Now let's name this instance. Okay, now what I would like to do here is to first of all get the position of the point from the second input. So it's vector pos is equal to point second input p0. Okay, and also let's get the normal direction, norm point 1 and 0. Right. Now let's also create some scale value as well, since you can also specify the scale value here for the instance. So p is the position, n is the normal, scale is xyz scale value, and you could also set some rotate as well, but I'm going to ignore these rotation for now. I'm just going to use this basic 3-parameter instance option. Okay, so I need a scale value here. Let's make some kind of interesting scale value. So vector scale, let's say I would like to create the scale value based on the y position, a y coordinate of the point position. So let's say it has to be vector, so you set, and the x and y become 1, and for the z scale, I'm going to use position y as a base, and there is a chance that this is going to be negative, so I'm going to make it as absolute value, and there is a chance that this is going to be 0 and minimum, so I'm going to add by 0.5. Okay, now I might want to set the same scale for the point copy to point, so that I be able to see the same result. So for the copy to points, what I could do is to set a vector scale attribute to each of the points from the sphere. So I'm going to create a point wrangle connected to this one. Let's say scale attrib. Let's copy the scale value, paste it right here, and the position right here should be a at p. And what I'm going to do is create a scale attribute for each of the point. Now as a result, the geometry that I got, it looks like this. So I would like to have the same geometry out of this loop using this instant function. Now I think I already have some necessary information to create a matrix from instance function. Let's try to do that. Matrix mat is equal to instance, first of all position, the normal and the scale. Okay, and use this matrix to transform the current point coordinate from this cone. Okay, so multiply by mat. And I have just changed one cone at each of the point. Now if I leave this loop, it looks like this, and it looks exactly the same as the one that I output from the copy 2 points. So I have just shown you that the one that I have just used, instance, can give you the exact result with the copy 2 points node. Now you might think that if it just gives you the same result, then maybe just using the copy 2 points is easier, but there's actually a benefit of using this instance node. One example I could give you is that since you have got this matrix value from the instance, you can use a function like cracktransform that I have shown you previously to get the rotation, scale, and translation out of this matrix, and use those values to create some lerp or interpolated values for the rotation, scale, and translation for the animation. I mean, just by using this copy 2 points, you cannot have any interpolated values from the original position to the copied position. But by having the matrix, you can actually create some interpolated values to create some kind of animated movement from one position to another. So that's the final exercise that I want to show you based on this simple code. Okay. So let's try to see how we can interpolate the matrix value from one position to another position, or one transformation to another transformation. Now I'm going to copy all these that I've just created and make it as a final exercise to make some interesting animations grown from this single cone to the final shape. Looks like this being animated. All right. Now let's see. To do that, what we need to do is to this is the final matrix transformation in order to move from one cone to this final shape, right? Now, in order to create an interpolated animation, you need to there is no such function to interpolate from one matrix to another matrix. So if you want to do some interpolation for the transformation, you first need to deconstruct this to a transform, scale, and rotation. Okay, now after you've done that, you can, for each of the transformation vectors, you can interpolate it, since that's just the vectors, right? But for the rotation, be careful not to use the vector interpolation, but instead it's better to use the quaternion interpolation using like S-lerp, like we just used in last sessions. So we're going to do that as well. And finally, we combine all these transformations back to the matrix and use that new matrix to transform the point. And as a result, you'll be able to create some animated grown animation. Well, let's see how we can do that. Okay, so first thing first, after we have this final matrix value, what I want to do first is to deconstruct this value into a scale, translate, and rotate using cracktransform that we have used. So to use that, first we need the TRS, which is the empty vector value to store, and then cracktransform. Now we don't know the order for the translation rotation or for the scale and also the rotation angle, but it could be anything. I mean, it's just the order is changing how the value is being changed. So the way the animation works might be different, but using any values for the X, Y, Z, and TRS should still work, because anyway you are having the final transformation, which is this one. Okay, so I'm going to do with the 0, 0 for the TRS and XYZ order. Now the pivot, I'm also going to set it as 0, shouldn't be the problem. And the mat is the one that I want to deconstruct or crack. And then TRS for the output parameters. Now as a result, you'll be able to fill in these TRS as a translation, rotation, and scale vector values. Okay, now let's create a float value called loop val to do the interpolation from 0 to 1. Let's name this loop val. So for this number, when it's 0, I want to show this base geometry previously being deformed, and when it's 1, I want to show the final geometry shaped like this. And by changing these sliders, I would like to create a interpolated movement of each of the geometry being going from the basic cone position to shape something like this. Okay. To do that, I need to create an interpolation for all translation, rotation, and scale. Alright, so let's start with a scale first. So vector SL loop, and I'm going to use the loop functions to create interpolation, and starting from a 1, 1, 1, okay, which was the original size, and the S is the final size that I've got here, and use the loop value to do the interpolation. Now let's also do the translation. So vector TL is loop starting from the 0, 0, 0 position, 0, 0, 0 position to T is loop val. Now the scale and translation is straightforward, but when it comes to rotation, first thing you need to do is to convert this rotation angle, which you get in a degrees for X, Y, and Z axis, into quaternion. Okay, and use S loop to do a loop for the rotation, because loop, the vector interpolation for the rotation is not like correct or precise, since it is being the angle ranges between 0 to 360 degrees, and if the value is going from 360 degrees to 30 degrees, if you just use the interpolate or loop, the value tries to go 360 degrees to 330 degrees by decreasing the value of 360 degrees, not by increasing it to reset it to 0. That's not what we want. So in order to make a smooth interpolation for the rotation, it's better to use quaternion. Okay, so first of all, I am going to change the R value, which is currently in Euler degrees value, into a quaternion using Euler to quaternion function. And I also need to use a radiance angle for this one. So first of all, I'm going to change the degree vector value into radiance vector value, and For the second parameter, which was, and let me check again, Euler to quaternion. Now this was the order for the angle rotation, and in this case I'm going to just use the XYZ order, which is equal to 0 if you look at this one. Okay, so I'm going to set it to 0. Now as a result, you'll be able to get a quaternion value which is vector 4. So vector 4, let's name this Q. Now I can now create a something like QL with a S lerp to create a interpolation between the current angle to the target quaternion, which is this one, and the current angle can be set as quaternion set 0, 0, 0, since there's no rotation here, and use Q for the target, and then lerp val for the interpolated value. Now now that I have a quaternion value, I would, in order to create a rotation matrix again, I would like to change this back to the Euler angle again. To do that, I can use a function called quaternion to Euler, and this one is inside the first parameter. It will be the quaternion, and the second input is again the rotation order, so I'm going to set 0, and as a result I'll be able to get the vector value, vector RL, okay, in radians. Okay, it should be QL. Okay. Now that I have enough information to do the transformation, but for all scale, translation, and rotation, it's time to define the order, in which order I should set the transformation, and it should be based on the order that I have defined here, which currently I have set as 0, which is equivalent to this one, starting from scale and then rotate and translate. So scale, rotate, translate should work. So in this case, I'm going to start by creating the matrix as an ident, then start with the scale format with SL that I've created right here, then rotate with the rotation, and the order is 0 again, then translate with TL. Okay, now I think it is ready to use this newly created matrix to multiply with the point coordinates. If I multiply it, when the lerp value is equal to 0, it shows the original cone position, but when I increase the value here, slowly it animates it to the final position for each cone. As you can see, it creates an interesting animation, which you cannot really get from just by using this copy to point node. So this is one of the benefits using a VEX instance function with all the other functions that I have shown you today, like these, together with some information from last session about quaternion. Makes this kind of really interesting animation pretty easily. And let's try to animate this, making this parameters based on a time frame as well. And let's end this session for today. So first of all, I'm going to create a value between 0 to 1. Then since I would like to make it as like a ping pong animation, so I'm going to use the trigonometry, and to do that, first I'm going to create an angle between 0 to 360 degrees, and then we'll use the cosine with that angle. We'll be able to create the value between 1 and -1 to 1. But I cannot use -1 for the interpolation, so I need to set it to 0 to 1. So I'm going to, and the last I'm going to use the fit to remap the value in between -1 to 1 to 0 to 1. Okay, and if I play it, I should be able to create this kind of growing, shrinking animation, which is based on this copy 2 points geometry, and using this instance function together with the cracktransform with the lerp. All right. Now this is pretty much it for what I wanted to show you today in this session for the basics of matrix. Now you can do a lot more things with the matrix, but I think it's enough for the one day. And other things you can do with the matrix a bit more complex and a bit more advanced, so I'm going to keep it for other videos. And before getting into the second session for the matrix, there are several stuff that I want to show you before. And the next topic I'm thinking to show you in this series, VEX for algorithmic design, is to use VEX to procedurally create point and primitives, which we have already done that several times using simple examples, but I would like to show you the exact way, that means the several types of ways to actually do it using VEX, so that you'll be more comfortable using VEX to create a procedural geometry inside a VEX, which is going to be a pretty essential things for a algorithmic design for sure. Okay, that's it for today. Thank you very much for watching. If you like the video, please like and subscribe to the channel. And I have also started the Patreon page myself, so if you find this video helpful or any other video helpful, please think about supporting me. I'll be really appreciated. Thank you very much, and see you next time. Bye bye.